Good afternoon, everyone. My name is Sajani Shrestha, and today I'll be presenting a predictive analysis of diabetes-related death counts in 2020. So this study focuses on how we can use time series forecasting techniques to better understand and predict diabetes-related mortality, especially during unprecedented times like the COVID-19 pandemic. So to begin, let's look at the background of this research. Forecasting plays a critical role in public health. It allows us to anticipate trends and respond proactively. And also, we explore three forecasting methods, which are the naive model, exponential smoothing, and also the area. So, naive model, which simply assumes the next value equals the last observed value, and the exponential smoothing, which captures something rather than systematically. And ARIMA, a more advanced model that handles complex patterns like autocorrelation and non-stationarity. So, with the added complexity of the COVID-19 pandemic in 2020, understanding the impact of chronic disease, diabetes is even more essential. So here is also shown like a problem presentation, which is the core of the study, which revolves around three objectives, which are accurate forecasting, pattern identification, and healthcare planning. So let's go one by one. It is accurate forecasting, which identifies the most reliable method for predicting death counts. And the second one is pattern identification, which understands if seasonal or structural factors influence mortality. And the third one is healthcare planning by using the insights to guide policy and services. So given the unpredictability of 2020, it was very crucial to assess whether advanced models truly offer better predictions or if simpler methods sufficed. So as you are seeing, the study not only creates a projection but also aims to ascertain whether seasonal or structural factors influence the death counts, which also guide the targeted measures that enhance healthcare readiness for upcoming crises. So the next slide is specification and design. So here's a quick review of forecasting methods used, which are the naive method, exponential smoothing, ARIMA model, and the modal evaluation. So the naive method served as a baseline, and which predict the future values. Obviously, will simply repeat the last observed one. And the second one is exponential smoothing. Which applied weighted average to capture short-term dynamics. And the third one is the ARIMA model incorporated differencing and the autoregressive components to manage trends and correlations. So for evaluation, we use two key metrics, which are MASE and RMSE, splitting the data set into the training set from January to September and a test set from October to December. So the next slide is the data acquisition. So our data set was resourced from the AS provisional diabetes death counts for 2020. So we aggregated monthly death counts to create an unvaried time series, and this transformed raw data into a format suitable for modeling. So all data processing and structuring were performed using R by ensuring it met the requirements for time series analysis. So there is given like a data aggregation and the data processing. So the next slide is data exploration. Now we explored the data. We applied moving average smoothing and different time series and autocorrelation analysis. So We applied moving average smoothing to visualize trends which showed a rise in deaths early in the year followed by a decline. So first order differencing was used to stabilize the data, a key step for models like ERIMA. Finally, autocorrelation analysis revealed short-term dependencies, justifying the need for differencing. The next slide is data transformation. Before modeling, we transform the dataset further, monthly aggregation and conversion into a time series object, and we conducted a stationarity test using the augmented decay Fuller test, which confirmed that the data was stationary after differencing, a crucial condition for ERIMA. So our choice of methods was intentional. The naive method offered a benchmark. Exponential smoothing was selected for its efficiency in handling short datasets like ours, and ERIMA was chosen for its flexibility, addressing trends and autocorrelation, though it required a careful tuning. So let's discuss the results. So the ADF test confirmed stationarity with a p-value of 0.01. When comparing models, surprisingly, the naive method outperformed both exponential smoothing and ERIMA, achieving the lowest RMSE and MASE scores. So the ERIMA model, despite its complexity, showed a highest error, demonstrating that in cases with weak trends and minimal seasonality, simpler models can actually be more effective. So they highlighted the risk of overfitting with advanced model in volatile datasets. Now let's do the short review of descriptive results of the project report. So the first one is ERIMA fitted versus actual. So you can see this plot shows the actual values of US deaths over time compared to the values fitted by the ERIMA model. So the black line represents the actual data trend, while the red line shows the fitted values from the ERIMA model. We can observe that the ERIMA model provides a fairly stable estimate, but the actual data fluctuates more significantly over time. So the second one is ACF of residuals. So this plot shows the ACF or autocorrelation function of the residuals from the ERIMA model. So most of the spikes are within the blue confidence bands, indicating that the residuals are mostly uncorrelated and the model has captured the main patterns in the data well. So the third one is residual histogram. This figure shows the histogram of residuals from our model. The residuals are spread fairly evenly around zero with some large positive and negative values. This pattern suggests that the residuals are roughly symmetrically distributed, but there are maybe slight deviations from normality. Last one is differenced series. This figure shows the differenced series over time. The plot highlights fluctuations around zero, indicating periods of increase and decrease, which helps in stabilizing the mean and making the data more suitable for time series modeling. So last one, I have concluded. So to conclude, our predictive analysis showed that the naive model was most reliable for forecasting diabetes-related deaths in 2020. As we also can see all the figures and the description of the results, the absence of strong trends or seasonality likely due to disruptions from COVID-19, which means that complex models like ERIMA did not offer better accuracy, which also indicates absence of complex trends or strong seasonality due to COVID-19 disruption. So this study reinforces an important relations, which are like in uncertain environments, simplicity can outperform sophistications. So ERIMA, which also shows that despite tuning, did not significantly improve accuracy. These insights are very valuable for healthcare planners, which are also especially when dealing with unpredictable crises where robust yet straightforward models can aid in quick decision making. So these all findings provide valuable insights for healthcare planning during uncertain times as well. So it also concluded the simpler models which have delivered better results in volatile situations as well. So all these study reinforces an important lessons within certain environments, which is like a simplicity can outperform sophistications. So that's everything I wanted to cover today. Thank you for taking the time to view my presentations. Thank you.